All right, guys. What we're doing today is more solving logarithmic equations, but it's not a whole lot different than what we did yesterday. As our main steps that we had yesterday still hold true for these here. One. So the steps we had yesterday still hold true for the ones we're solving today. One, we need to get one expression on either side. Two, we need to get the variable or variables out of the power or log. And then three, we're going to solve. Now the issue that we have with this one here today is that the left side has two terms, the right side has one. Now our product property of logarithms stated that if we have two things being multiplied together inside the log, so log base m times n is the same as log base b of m plus log base b of n. So if we have two logs being added together, we can rewrite it as a single log with what's inside being multiplied. So, log of 2x plus log of x minus 5 is the same as log of 2x times x minus 5 equals 2. So now we do have one term on either side. Now we can solve it the exact same way we solved these at the end of the lesson yesterday. We can put both sides to the base of the log. Since the log here, the base is not written, it's understood to be 10. If the base of a log is not written, it's understood to be 10. And we put this to the base of 10, these will cancel, leaving us with 2x times x minus 5 is equal to 10 to the second power, but 10 squared is 100. Questions on this here? At this point here, we do need to distribute the left side of this here. 2x times x is 2x squared. 2x times negative 5 is negative 10x. Now, since we do have an x squared term, we will need to get this equation equal to 0. So we can subtract 100 from both sides. Telling us that 2x squared minus 10x minus 100 is equal to 0. Now we get it to this point here to be able to solve for the value of x. Now there's two main ways we can go about, or three. We can factor it, graph it, or use the quadratic formula. Now if we go about factoring this here, the first thing we'll want to do is factor out the greatest common factor between these three terms. And the greatest common factor between these three terms is 2. So we can take the 2, factor it out of 2x squared and get x squared. We can factor the 2 out of 10x and get 5x. And 2 factored out of 100 is 50. At this point here, we'll have our 2 sets of parentheses with 3 spaces. Now, since the third term is negative, our signs are opposite, plus and minus. The factors of x squared, well, the only factors of x squared are x and x. Now, our factors of 50 are 1 and 50, 2 and 25. 3 is not a factor, 4 is not a factor, but 5 and 10 are. And the factors that we're going to want are 5 and 10. Telling us the factored form is 2 times x plus 5 times x minus 10. Now, according to our zero product property, anytime we have 2 or more things multiplied together to equal 0, one of those has to be 0. So either x plus 5 is 0 or x minus 10 is 0. With our x plus 5, we can now solve for x. Subtract 5. Telling us x is negative 5. With our x minus 10, we can add 10 to both sides, telling us x is equal to 10. Questions on this here? The other option we had for solving this quadratic equation is graphing. So we could say 2x squared minus 10x minus 100 and graph it. Second table. We do see at negative 5, the y value is 0. It's one of the solutions. And if we scroll down to 10, we see that the y value is also 0. Questions on how we found these here? Now, we do need to check these and make sure that they both work, because we do have x equals negative 5, x equals 10. Because as we talked yesterday, the values that we end up with inside the log cannot be 0 or negative. If one of our values of x makes one or both of these be 0 or negative, we have to throw that solution out. So if we start with 10, plugging it in for x. So the first one, we have log of 2 times 10. Well, 2 times 10 is 20. And 10 minus 5 is 5. So after we plug 10 in and simplify, we get log of 20 plus log of 5. Both positive, and those will work. And we can plug it in either calculator. Log of 20 plus log of 5. Not 5. Yeah, no, it is 5. Is 2. That's what it said it was. What we were wanting to say, so that works. Let's do this again with negative 5. Well, log of 2 times negative 5 is negative 10. Negative 5 minus 5 is negative 10. I cannot have 0 or negative inside the log. Here I have 2 different spots where I have a negative number inside the log. Log of negative 10 we cannot take. So that tells us x equals negative 5 is one of our extraneous solutions. So even though we did have 2 answers, the only one that works for this is 10. X equals 10 is our only solution for this here. That won't always be the case, that the negative one is the restriction, is our extraneous solution, not restriction, extraneous solution. But in some cases it is. Questions on this here? Well, let's look at this one here. Log base 6 of 6x plus log base 6 of x minus 1 equals 2. Again, just like with the last one, we need to condense these two expressions down to 1, because if we can have it as 1, we can solve this. And our product property states that we can write the sum of two logs with the same base as a single log, with what's inside each of those logs being multiplied. So it gives us 6x times x minus 1. Now to simplify the log, we're going to put both sides to the base of 6. And that's because we want this log base 6 to simplify. And by putting it to the base of 6, it is going to simplify out, leaving us with just 6x times x minus 1 is equal to 6 to the second power. Now what is 6 squared? 36. Now we just need to simplify some stuff on the left, so we'll distribute 6x times x is 6x squared. 6x times negative 1 is negative 6x. Yes. We got it equal to 0. So this one here we'll graph first. 6x squared minus 6x minus 36. Graph. We do see that it crosses the x-axis in two places, and they are nice places. They're going to cross at integers. And if we look at the table, our two spots that it crosses are at negative 2 and 3. Because we're looking for what values of x will make the y value be 0. Now, if we wanted to factor it, we can. The first thing we would do is factor the 6 out, giving us x squared minus x minus 6. Since the 6 is negative, our signs would be opposite. Only factors of x squared are x and x. And the factors of 6 that we would want are 2 and 3. But here, just like with graphing, we get the exact same answers as 3 and negative 2. But again, we do need to check and make sure that these work. Well, let's try negative 2 first this time. Well, 6 times negative 2 is negative 12. Negative 2 minus 1 is negative 3. This is not going to equal anything because we can't take...
May I have your attention? May I have your attention, please? Whoever borrowed the office keys, would they please return them at this time? Whoever borrowed the office keys, would they please return them at this time? Thank you.
Can I take log base 6 of negative 12 or log base 6 of negative 3? Those just don't work. We can't take the log of a negative number. Now, the reason we get it is that product, because negative 3 times negative 12 is positive 36. Log base 6 of positive 36 works. But the actual answer of value negative 2 doesn't work because in each individual log, we don't have a value for that. So in the original problem, it doesn't work. So negative 2 is out. It is still good to check 3 log base 6 of 6 times 3 plus log base 6 of 3 minus 1, just to make sure that this doesn't also give us a negative on one of the two. 6 times 3 is 18. 3 minus 1 is 2. And this does work. We don't have negatives. We can plug this in and see that, yes, this does give us 2. So x equals 3 is our only solution that works. Questions on these here? I think for the most part, at this point, hopefully we've seen the only real difference from what we're doing today and what we did at the end of the class yesterday is combining or rewriting this first expression as a single term. Questions on this here? We feel comfortable with how this works? Okay. I want to show one of these here. We can look at this one. This one's a little different. We won't see this on the homework. I wanted to show us this so that we've at least seen it. It is possible to have addition and possible to have subtraction. Now, subtraction's a little bit different. Because log base b of m minus log base b of n is equal to log base b of m divided by n. If we have two logs with the same base being added, we can rewrite it as multiplication inside. Two logs being subtracted, we can rewrite it as the 2 being divided inside the logarithm. So this textbook and most don't do a whole lot with this property. We show the addition property with multiplication, that's fine. Not a lot to it. This isn't anything harder. It's just that, okay, we have division, we have a fraction we'll have to work with. Properties still hold the same, steps still hold the same. Because our next step after we get one term on either side is to get rid of that log. So we'll put both sides to the base of 4. This cancels out, telling us that we have x over x minus 1 is equal to 4 to the 1/2. And 4 to the 1/2 is 2. Because we haven't had a chance to go over this yet, but 1/2 power is the same as the square root. Now the next step we're going to do is to really get rid or simplify this fraction. And to do that, we're going to multiply by our least common denominator, our rational chapter, the chapter we did before this. Because if I multiply this left side by x minus 1, it and the x minus 1 on the bottom will simplify out. We're dividing it by itself after we multiply it. But if we do it to one side, we have to do it to the other. So the left side is left with just x. The right side will multiply through. 2 times x is 2x. 2 times negative 1 is negative 2. Question so far. Do we have an x squared term? Or an x to a power greater than 1? Well, no, right? We just have x. Get x by itself. We don't have to get this equal to 0. So we could subtract 2x from both sides, leaving the only term left on the right-hand side, negative 2. X minus 2x, negative x. Now there's two ways we can go from this here to our final answer, because we don't want to know what negative x is. We want to know what positive x is, yes? Well, if negative x is equal to negative 2, positive x should equal positive 2. If I flip the sign on one, we flip the sign on the other. Or we can just multiply everything by negative 1 to get the signs to change, or divide both sides by negative 1. Same thing. And that's our only solution. Now we could plug it back in and make sure we don't get any negatives. Taking log base 4 of 2 minus log base 4 of 2 minus 1, trying to get to 1/2. Well, the first one is just log base 4 of 2. There's nothing to simplify inside the parentheses. 2 minus 1 is 1. Log base 4 of 1 is 0. As an exponential, it's one of the log base b of 1 equals x is really exponentially saying b to what power is 1. Well, anything to the 0 power is 1. So if we end up with a logarithm with 1 inside of it, it's going to be 0. So really all we're left with is log base 4 of 2, which is indeed 1/2. Makes sense? I don't see it come up. This is more college algebra might show it. This might come up, but above and beyond. Questions over anything we've done today? So I think y'all have this one on your note sheet, yes? So flip to it. Right below it, write this. Because this is the last problem we're going to do today. I want to bring this one up because it's not any different than what we've done so far. There's just one main difference we have to deal with when solving. And that's partially because of the natural logs. Now, first main steps, everything is going to be the same. Since we have two logarithms being added, we can rewrite it as a single log with what's inside being multiplied. Now the base of natural logs is what? E, yeah. So just like the same thing as we did before, we'll put both sides to the base of e, so that e to the natural log will simplify, leaving us with x times x minus 5. E to the third power. Is that going to be a nice number? No. E is irrational, so an irrational number to a power is still going to be an irrational number. So we have to leave it as e to the third. Now we still need to simplify the left-hand side. So we'll distribute x. X times x is x squared. X times negative 5 is negative 5x. Equals e to the third power. Since we do have a variable, or to a power greater than 1, we have x squared. We will need to get this equal to 0. Now the main reason I bring this one up, and we look at this one here, is that it's not possible to factor this here. It is possible to graph it, but we have to do a little bit more than just graph and look at a table. And that's because e is a irrational number. Third time charm. There we go. Because e to the third power is this here. So we could try approximating it to 3 decimals or leaving it as e to the third. Either way, we will have to use the quadratic formula to solve this here. We have to use the quadratic formula. And this is matching up to our ax squared plus bx plus c. So the first thing we have is negative b. Well, negative, our b value is 5. Plus or minus the square root of b squared, so we have negative 5 squared, minus 4 times our a. Well, a is the number in front of x squared, which is 1. And c is going to be negative e to the third, because e cubed is a number. We leave it as e because e is irrational. It's a non-repeating, non-terminating decimal. So there's not a whole lot of reason to try to write it or approximate it if we're going to have to plug everything into the calculator later. And it's a little bit easier just to write e than that big old decimal number in here. All over 2a. Well, 2 times 1. At this point here, there's a few things we can clean up. The negative 5 is going to be 5. On bottom, 2 times 1 is 2. Now inside the radical, we can't actually combine the 5 squared and 4 times 1 times negative e to the third because the e to the third is an irrational number. Now negative 5 squared is 25. Our negative 4 times 1 is negative 4 times negative e to the third is going to be plus 4e to the third. So this is as simplified as we can get it without converting to decimals. Questions on how we got here? I can pause a second if you need. Now we will need to calculate this out a little bit further because all the ones that we've done, especially with 2 logs being added, one solution's worked, one is not. And it's figuring out which one works and which one doesn't. Well, there are 2 equations here. Because we have 5 plus the square root of 25 plus 4e to the third over 2. And the other x is equal to 5 minus the square root of 25 plus 4e to the third over 2. Okay. I'm going to scroll back up to the top, and if we look at this here, natural log of x, is there anything being multiplied by that x inside the log? No. And we said that we cannot have one or both logs be negative, yes? So if the value of x is negative, most likely it's going to be one of our extraneous solutions because there's nothing inside here to take that negative value and make it positive. If it had been negative x, okay, that's going to make it positive. Then the positive would have been the extraneous solution. So most likely, whichever one of these is negative is going to be our extraneous solution. Most likely, if there is going to be one, it'd be the one with the minus. But just to make sure, we can take the calculator and say 5 plus square root of 25 plus 4 second ln gives us e to the third over 2. 7.632. So x is approximately 7.6632. So most likely that is the solution that works. Now, the nice thing with both of these calculators is if we scroll up and hit enter, it'll retype the whole thing in. And I can come back and change that plus to a minus. That way I don't have to retype the whole thing back in. Makes it a little bit nicer. Negative 2.632. The negative 2.632 is not going to work because when we plug it in that first part, ln of negative 2.632, we'll end up with a negative inside the log. That's an extraneous solution. We throw it out. Questions on this here? X minus 5. Now we could check the other one. ln of 7.632 plus ln of 7.632 minus 5. So I just plug that value of x back in. And what should we get? We should get 3, yes? It's not going to give us exactly 3. It'll give us something close to 3. And the reason it gives us something close to 3 and not 3 is because, well, let's look back up, was the value of the one we wanted, this here, exactly 7.632? Well, no, there's a whole bunch of other digits there, yes? The more digits we include in our answer, the closer it'll get. Let's store that value into x. So if we took ln of this value plus ln of this value minus 5, it'll give us 3. We have to plug in enough digits to get it there. And 3 digits is not enough. Questions on this here? You ready for the really, really big assignment? That's it.